in various ways. For one, laboratory starts, and some of you folks will of course be involved in that activity. Be sure you're appropriately attired, got your safety glasses on, lab book in hand, otherwise you can't get in the class. So be sure you're ready to go. Everybody get one of these? We dished them out in class on Friday. Intended to assist your ability in short order fashion to get at writing principal system inventories correctly. Anybody else? Anybody else? I remind you again, particularly you folks who just got a copy of this, what goes on Friday is an integral part of this gathering. You need to be there. If you don't, you're going to miss new material. You can't afford to do that in this game. As we said, what goes on in class, Fridays included, defines the course. That's it. Before I proceed, those of you who indicated an interest in functioning as note takers, please, at your earliest convenience, go to the DRC, which is Reed Hall 001. The address for that is in the syllabus, and announce to them your intentions. They might ask you for what class, you know what that is. So, we get on with equilibrium, chapter 17. Wrap that up, and then you've already been provided foundation in chapter 18, so we'll pick it up from your point of foundation when we finish our comments on chapter 17. For 1711, that's the temperature that you will obtain if you calculate such correctly using this. The so-called ideal gas law. For 1712, if you solve 1712 equilibrium by factoring, as is indicated in the notes, you will, of course, as exists for any quadratic equation, get two roots. But only one of these roots is real. Both satisfy the relationship arithmetically, but only one of these roots satisfies the relationship chemically. Did you recognize that? I trust you read over that. Concentrations cannot be zero or negative. That makes no sense at all. So, keep that in mind when you solve problems of this nature. Now let's take a look at challenge problem 17.1, which illustrates the speculation method, which is discussed in the notes just before the challenge problems. You might just as well call the speculation method the horse sense method. What the horse sense method, the speculation method, is based on is making, as well as you can, horse sense assessments of what kind of numbers you can get when you solve equilibrium problems. For example, we just mentioned such a case, 1712, where the problem arithmetically has two roots, but chemically it only has one root. So what we have to say further about the speculation method, I think, will be more straightforward when we in fact tackle the problem, rather than me giving you some lecture on this. Let's take a look again at this equilibrium system. Earlier on in chapter 17, we looked at this equilibrium system with the equilibrium reaction written in the opposite direction. Now, if for an equilibrium reaction, I have a K value, and I choose to consider this equilibrium reaction in the reverse direction, I still have a legitimate equilibrium. If I do that, what happens to the K value? It inverts, becomes reciprocal if you prefer. Now, to try to keep arithmetic as simple as possible, so that when we do these illustrations of equilibrium system analysis by calculation, I want you to be able to focus on the chemistry, so I keep the numbers as simple as possible when I can do such. So we'll look at this equilibrium system, imagining that it's studied under temperature conditions for which the Kc value, C, equilibrium constant expressed in terms of molar concentration, is 1.0. I don't think you can get any simpler value than that from a numerical standpoint. If initially this equilibrium system lives in this piston cylinder gadget in a contained volume of 1.0 liters, and I tell you that with this equilibrium existing in this contained volume of 1.0 liters, we have 1 mole of nitrogen and 1 mole of hydrogen. How much ammonia must we have? Got to be 1 mole. That's the only way the equilibrium constant value of 1.0 can be satisfied. Which means, since the volume is 1.0 liters, which allows us the liberty of recognizing that for this system, since the volume is 1.0 liters, molar concentration and mole amounts are numerically equivalent. That makes the arithmetic as simple as possible. Nitrogen molarity 1.0, hydrogen molarity 1.0, which establishes that the ammonia molarity must also be 1.0. Now let's take some action on this system. I take a hold of the handle on the piston. Push it in until I reduce the volume to 0.50 liters. And then by some mechanism or device, I lock the piston in place, which means I've changed the volume from 1.0 liters to 0.50 liters as a consequence of raising the pressure to do just that. When I make this change, this equilibrium still alive? This equilibrium exists as I make this change? Or is the equilibrium, at the instant at which I made the change, is the equilibrium killed? The equilibrium is killed. Hey, clearly, I change every concentration, don't I? Now, when I kill this equilibrium by changing the concentration, what reaction has got to take place to get us back to equilibrium? Is it left to right? Or is it right to left? We talked about this before. You can look at the equilibrium reaction and apply a mole count consideration to it. If I take these coefficients as representative of moles, I'm looking at 2 moles on the left and 4 moles on the right. I reduce the volume. Which way shall I proceed if I reduce the volume? Toward more moles or fewer moles? Toward fewer moles. So the reaction that's got to take place to get us back to equilibrium is this. Now another way you could look at that from a number analysis standpoint is by way of reaction quotient, which is symbolized with a fancy Q. Did you read about reaction quotient in the chapter 17 discussion? It's your job to read this stuff. Let's take a look at this from a reaction quotient analysis standpoint. I reduce the volume by a factor of 2, and before any reaction takes place to get us back to equilibrium, what's this molarity? After having reduced the volume, but before reaction occurs to get us back to equilibrium, what's this molarity?
1.5. 2.
2! I still got a mole of this, but now it's contained in a volume of 0.50 liters. Okay? So, it's 1.0 moles over 0.50 liters. The molarity is 2. What's the molarity of this? And the molarity of this? Oh, become 2. I doubled the molarity of every one, and I had a mole each to start with. Okay? So I got 2 times 2 cubed divided by 2 squared. Watch out, this is pretty tough arithmetic. I'm pushing the buttons on my calculator. What do I get? I don't want to see any push button devices in operation to answer this.
4.